Imagine an aircraft so fast it could take off from New York, and before you finished your morning coffee, it would already be approaching Moscow. Not a missile, not a rocket. An actual piloted aircraft carrying enough nuclear weapons to level an entire nation. This wasn't science fiction. This was the XB-70 Valkyrie, and it remains one of the most ambitious and terrifying engineering achievements in human history. Here's what makes this story extraordinary. The United States spent billions of dollars developing this incredible machine. They pushed the boundaries of aerospace engineering further than anyone thought possible. They created technologies that seemed like they belonged in the next century. And in response, the Soviet Union didn't just build one aircraft to counter it. They built an entire fighter fleet. They developed new missile systems. They restructured their entire air defense network. All because of this single American bomber that could outrun almost anything in the sky. But here's the twist. By the time the Soviets had finished building their response, the Americans had already canceled the XB-70 program. The fighter jets designed specifically to shoot it down would never face their intended target. It's one of the most expensive games of chess ever played, where both sides made massive moves. And then the board was simply put away. If you find Cold War aviation as fascinating as I do, make sure to hit that subscribe button and give this video a like. I spend countless hours researching these incredible stories, and your support helps me bring more of them to you. So let me take you back to the late 1950s. The Cold War was at its most intense. Both superpowers were locked in a race that went far beyond just nuclear weapons. They were competing in technology, in ideology, in every measurable domain of national power. And in the realm of strategic aviation, the Americans had identified something that kept them awake at night. You see, the existing fleet of B-52 Stratofortresses, while capable and reliable, flew at subsonic speeds and relatively modest altitudes. Soviet air defenses were improving rapidly. Surface-to-air missiles were becoming more accurate. Fighter interceptors were getting faster. American military planners charted the trajectory of Soviet defensive capabilities and saw a troubling future. Within a decade, they calculated the B-52 would become increasingly vulnerable to interception. It would become a sitting duck. The solution, they believed, was speed and altitude. If you could build a bomber that flew so high and so fast that no existing weapon system could catch it, you would essentially have an untouchable nuclear delivery platform. This wasn't just military theory. This was existential strategy. The ability to guarantee nuclear retaliation was the foundation of deterrence. And deterrence was the only thing standing between civilization and annihilation. I want you to understand the technical challenge here, because I think it's genuinely underappreciated. In 1955, when the Air Force issued the requirement for what would become the XB-70, they were asking for an aircraft that could cruise at Mach 3. That's 3 times the speed of sound. That's over 2,000 miles per hour. At that speed, air friction heats the aircraft's skin to temperatures exceeding 600 degrees Fahrenheit. Aluminum airframes would simply melt. No existing engines could sustain that speed. No known materials could handle that kind of heat for hours at a time. They were essentially asking industry to invent an entirely new category of aircraft using materials and technologies that didn't even exist yet. And somehow, North American aviation said yes. The engineering team that assembled to tackle this challenge included some of the most brilliant minds in aerospace history. They faced problems that had never been solved before. How do you build an airframe that can withstand 600-degree temperatures for hours? You use stainless steel honeycomb construction and titanium. But working with these materials at this scale had never been done. They had to invent new welding techniques, new fabrication methods, new everything. How do you create engines powerful enough to push a 400,000-pound aircraft to Mach 3? You develop the General Electric YJ93, each producing 30,000 pounds of thrust with afterburner. 6 of these monsters would power the Valkyrie, but these engines didn't exist when the program started. They had to be created from scratch. How do you maintain stable flight at 3 times the speed of sound? At these velocities, traditional aerodynamic principles behave differently. The XB-70's designers came up with a revolutionary solution. They designed the wingtips to fold downward during supersonic flight up to 65 degrees. This wasn't just for stability. It actually captured the shock wave produced by the aircraft's nose and used it to generate additional lift. They called it compression lift, and it was a concept that had never been implemented in a production aircraft. The delta wing configuration spanned 105 feet. The fuselage stretched 185 feet longer than a Boeing 737. The vertical stabilizers rose to a height of 30 feet. When you look at photographs of the XB-70, what strikes you is how alien it appears, even by today's standards. It seems like something that should exist 50 years from now, not something that flew in 1964. The fuel system alone was a marvel of engineering. The XB-70 carried over 40,000 gallons of JP6 fuel, special high flashpoint jet fuel developed specifically for high-temperature applications. At Mach 3, the fuel served a dual purpose. Beyond simply powering the engines, it acted as a heat sink, absorbing thermal energy from the airframe before being burned. This thermodynamic balancing act required precise engineering of the fuel flow systems. The cockpit design tells you everything about how far beyond normal aviation parameters this aircraft operated. The two crew members sat in escape capsules rather than traditional ejection seats. At Mach 3, conventional ejection would have been fatal. The air density at that speed would have killed any pilot instantly. So the engineers designed capsules that would close around the crew members, protecting them from the blast of hypersonic air. These capsules could be ejected and would descend by parachute, theoretically allowing survival even at maximum speed. It was an acknowledgement that this aircraft existed in a realm where the normal rules simply didn't apply. The navigation and bombing systems were equally advanced. Its XB-70 used an inertial navigation system combined with a sophisticated radar system that could map terrain and identify targets. Remember, this was decades before GPS. The aircraft had to be capable of flying thousands of miles, finding a specific target, and delivering its weapons with precision. The computational systems required to accomplish this task were cutting edge for their era. Speaking of weapons, let me tell you about what the XB-70 was designed to carry. The internal weapons bays could accommodate up to 14 nuclear bombs. The primary weapon would have been the B-1 thermonuclear bomb, the most powerful weapon ever deployed by the United States. A single B-41 had a yield of approximately 25 megatons. To put that in perspective, that's over 1,600 times the power of the bomb that destroyed Hiroshima. A single XB-70 could have carried more destructive power than all the explosives used in World War II combined. This brings me to something I think is worth contemplating. When we talk about these aircraft as engineering achievements, it's easy to lose sight of their purpose. The XB-70 was designed to end civilization. Its mission profile assumed the destruction of entire cities, the deaths of millions, the initiation of a nuclear exchange that could have exterminated humanity. The brilliant engineers who created this magnificent machine were building the ultimate instrument of mass death. I don't say this to condemn them. They were working within the context of their time, trying to protect their country from what they saw as an existential threat. But I think it's important to hold both truths simultaneously. The XB-70 was a remarkable achievement and a terrible weapon. Its beauty doesn't diminish its horror. Its horror doesn't diminish its beauty. Now I need to explain something about the strategic thinking of this era, because I think it's crucial to understanding why the XB-70 seems so necessary. In the late 1950s and early 1960s, intercontinental ballistic missiles were still in their infancy. They existed, yes, but their accuracy was questionable. Their reliability was uncertain, and their numbers were limited. Manned bombers were still considered the primary nuclear delivery system. The logic went like this. A manned bomber could be recalled. A missile, once launched, could not. A bomber crew could assess the situation, confirm targets, even abort the mission if circumstances changed. A missile was simply a projectile. In an era when communication systems might fail, when false alarms might occur, having humans in the loop seemed essential. And if you're going to rely on manned bombers, you need bombers that can survive to reach their targets. The XB-70 would fly at 70,000 feet, far above the practical ceiling of any 1950s fighter jet. It would cruise at Mach 3 faster than any operational interceptor. It would carry nuclear weapons capable of destroying any target on Earth, and it would be essentially invulnerable to anything the Soviets could throw at it. At least that was the theory. But the Americans weren't the only ones watching the skies. What I find remarkable about the Soviet response is how seriously they took the threat. Remember, the XB-70 was still on the drawing board when Soviet intelligence first learned of its existence. The aircraft wouldn't fly for years, but the implications of an American Mach 3 bomber were so alarming that the Soviet military began developing countermeasures immediately. The challenge facing Soviet engineers was unprecedented. How do you intercept an aircraft flying at 70,000 feet at 3 times the speed of sound? Your interceptor needs to fly even higher and faster to achieve a firing solution. The GI forces involved in such intercepts would be extreme. The reaction time available would be minimal. The technical requirements seemed almost impossible, yet the McCoy and Gurevich Design Bureau accepted the challenge. What emerged would become one of the most legendary aircraft of the Cold War era, the MiG-25 Foxbat. The MiG-25 fascinates me almost as much as the XB-70 itself. Here was an aircraft designed with a singular purpose, to kill a specific enemy aircraft that didn't even exist yet. Every design decision, every engineering choice, was made with the XB-70 in mind. The development timeline is remarkable. The Soviet government issued the requirement for a new high-altitude interceptor in 1961. The same year, the Americans canceled the XB-70 as a weapon system. But the Soviets didn't know about the cancellation. Their intelligence indicated that America was building a fleet of Mach 3 bombers, and they responded accordingly. So they built the Foxbat anyway. The design that emerged was unconventional by Western standards. The MiG-25 had enormous wings for its weight, giving it excellent high-altitude performance. Its twin engines were positioned close together in the rear fuselage, giving the aircraft a distinctive appearance. The large rectangular air intakes on either side of the cockpit could swallow enormous quantities of air, feeding the hungry engines during high-speed flight. The Soviets faced their own material challenges. They needed an aircraft that could reach Mach 2.8 or higher. That meant dealing with the same heat problems that plagued the XB-70. But the Soviet aviation industry didn't have the same access to titanium that the Americans had. Titanium was expensive, difficult to work with, and in limited supply. So Soviet engineers made a different choice. They built the MiG-25 primarily from nickel-steel alloys. This made the aircraft heavier than an equivalent titanium design would have been. Soviet engines were powerful, and weight could be compensated for with thrust. The resulting aircraft was a brute machine of raw power, rather than elegant efficiency. It carried 2 massive Tamansky R-15 engines, each producing over 22,000 pounds of thrust. The avionics were similarly unconventional. The MiG-25's radar, the RP-25 Smerch, was one of the most powerful ever fitted to a fighter aircraft. Its enormous antenna could detect targets at ranges exceeding 100 kilometers. But this power came at a cost. The radar's vacuum tube design was chosen for reliability and resistance to electromagnetic pulse effects from nuclear detonations. But it was heavy and consumed enormous amounts of electrical power. I want to emphasize something about the Soviet engineering philosophy here, because I think it reveals important cultural differences. American engineers of this era tended to optimize for elegance and efficiency. They sought the most sophisticated solution, using the most advanced materials and techniques available. Soviet engineers, by contrast, often optimized for robustness and manufacturability. They asked not just whether something could work in ideal conditions, but whether it would work in the harsh conditions of actual Soviet military service. The MiG-25 embodied this philosophy. It wasn't the most elegant aircraft ever designed. Its heavy steel construction, its thirsty engines, its powerful but primitive radar, all of these were compromises. But they were compromises that worked. The aircraft could be built in large numbers using existing Soviet industrial capacity. It could be maintained by conscript mechanics with limited training, could operate from austere airfields in the Soviet periphery. The MiG-25 could reach speeds of Mach 2.83 in operational configuration, test flights without weapons. It reportedly exceeded Mach 3. Its service ceiling was over 67,000 feet, with some sources claiming it could reach 80,000 feet in zoom climbs. For its intended purpose killing, the XB-70 would have been devastatingly effective. But here's what makes this story even more interesting. The Soviets didn't stop with just the MiG-25. They simultaneously developed an entirely new generation of surface-to-air missiles. The S-200 NATO designation SA-5 Gammon was specifically designed to engage high-altitude, high-speed targets. It could reach aircraft at altitudes exceeding 100,000 feet and speeds beyond Mach 5. Multiple variants were produced with different guidance systems and warhead configurations. The Soviet air defense network was restructured around the threat of high-speed, high-altitude penetrators. Radar systems were upgraded, command and control procedures were revised, training programs were modified. Billions of rubles were spent preparing to counter an aircraft that in some ways represented America's ultimate conventional weapon. I want to pause here and consider the economics of this situation because I think it reveals something important about Cold War dynamics. The XB-70 program ultimately cost the United States approximately $1.5 billion in 1960s money. Adjusted for inflation, that's over $10 billion today, and only 2 aircraft were ever built. The Soviet response likely costs even more. The MiG-25 program alone produced over 1,100 aircraft. The S-200 system was deployed in hundreds of batteries across the Soviet Union and Warsaw Pact nations. The radar upgrades, the training, the infrastructure, the ongoing operational costs, all of this added up to an enormous investment. And here's the crucial irony that I keep coming back to. The XB-70 was canceled in 1961 as a weapon system before the first prototype even flew. The reasons for cancellation had nothing to do with Soviet countermeasures. American strategic thinking had simply evolved. By the early 1960s, intercontinental ballistic missiles had matured into reliable weapons. The Minuteman missile program was proceeding successfully. Nuclear submarines carrying Polaris missiles provided an essentially invulnerable second strike capability. The need for a manned supersonic bomber seemed less urgent when you had missiles that could reach Moscow in 30 minutes from underground silos in Montana. There was also a growing recognition that the XB-70's supposed invulnerability might be temporary. Soviet SAM technology was advancing rapidly. The same speed and altitude advantage that made the Valkyrie seem untouchable in 1955 looked less certain by 1961. Perhaps military planners reasoned the money would be better spent on missiles. President Kennedy's Secretary of Defense, Robert McNamara, was particularly skeptical of the XB-70. He favored systems that could be analyzed quantitatively, and the Valkyrie's cost-effectiveness simply didn't add up when compared to ICBMs. In March 1961, he announced that the XB-70 would continue only as a research program, not as a weapon system. The Air Force's dream of a Mach 3 bomber fleet was over before it began. But the prototypes were already under construction. They would eventually fly. The first XB-70, tail number 62-1, took to the skies on September 21, 1964, from Air Force Plant 42 in Palmdale, California. What happened next exceeded everyone's expectations. The test pilots reported that the Valkyrie handled beautifully. Despite its immense size and revolutionary design, it flew with remarkable stability. On subsequent flights, it achieved Mach 3 cruise sustained for extended periods. It demonstrated that an aircraft of this size and speed was not only possible, but practical. The engineering worked exactly as designed. I've read accounts from the test pilots, and what strikes me is their genuine amazement at what this aircraft could do. Imagine sitting in that cockpit, watching the Mach meter climb past 3, knowing that you're traveling faster than a rifle bullet. The airframe groaning under thermal stress, the ground below becoming a blur. The curvature of the Earth visible at the edge of your vision. 6 afterburners roaring in unison behind you. You're flying at the edge of space, faster than almost anything that has ever flown. The second prototype, tail number 620207, joined the flight test program in July 1965. Together, the two Valkyries accumulated over 250 hours of flight time, gathering invaluable data about sustained high-speed, high-altitude flight. This data would inform aerospace engineering for decades to come. For 2 years, everything went according to plan. Then came June 8, 1966. It was supposed to be a routine photo flight. General Electric, which had built the engines, wanted publicity photographs of the Valkyrie flying in formation with other aircraft powered by their engines. Simple formation flying, nothing technically demanding. 5 aircraft flew together that morning: the XB-70, an F-4 Phantom, an F-5 Freedom Fighter, a T-38 Talon, and an F-104 Starfighter.
NASA pilot
Joe Walker, one of the most accomplished test pilots in history, a man who had flown the X-15 to the edge of space, was flying the F-104. He was positioned just behind and slightly below the Valkyrie's right wing. What happened next has been analyzed countless times. The exact cause remains somewhat disputed. The F-104, apparently caught in the Valkyrie's powerful wingtip vortex, rolled and struck the XB-70. Walker's aircraft exploded instantly. The collision destroyed both of the Valkyrie's vertical stabilizers. For several seconds, an eternity, the massive bomber continued flying, seemingly stable. Then the aerodynamic forces took over. The XB-70 entered an uncontrollable flat spin, rotated slowly like a falling leaf, but at hundreds of miles per hour, the horizon spinning, the desert floor rising. Co-pilot Carl Cross was unable to eject. He died in the crash. Pilot Al White managed to escape, his capsule firing him clear of the doomed aircraft, but his injuries were severe. Joe Walker was killed instantly in the initial collision. In a single moment, a routine photo flight had claimed 2 lives and effectively ended the XB-70 program, the remaining aircraft. Number 1 continued flying until February 1969, when it was retired to the National Museum of the United States Air Force in Dayton, Ohio, where it remains today. If you ever have the chance to see it in person, I highly recommend it. Standing beneath this aircraft, you get a sense of its impossible scale, its futuristic lines, its absolute ambition. The Valkyrie was gone. But its influence was just beginning. What happened to all the technology that was developed for this program? Because here's the thing, the XB-70 was canceled as a weapon system. But the engineering breakthroughs it pioneered didn't disappear. They filtered into other programs, other applications, other aircraft. The compression lift concept that the Valkyrie demonstrated influenced subsequent aircraft design. The folding wingtips, while not widely adopted, showed that variable geometry could enhance supersonic performance. The high-temperature alloy construction techniques developed for the XB-70 found applications in other aerospace projects. More importantly, the flight data gathered by the 2 Valkyries contributed enormously to our understanding of sustained high-speed flight. When you're designing the next generation of aircraft, you need data. You need to know how materials behave under real conditions, how aerodynamic theories translate into practice, how systems perform over extended operations. The XB-70 provided this data. The supersonic transport programs of the 1960s and 70s, both the American SST project and the Concorde drew on XB-70 research. It's the space shuttle, which had to withstand similar thermal stresses during re-entry, benefited from knowledge gained during Valkyrie development. Even modern hypersonic research can trace some of its roots back to the XB-70 program. But let me return to the Soviet side of the story, because I think there's an important lesson here. The MiG-25 was developed specifically to counter the XB-70. When the XB-70 was canceled, the Soviets suddenly had an incredibly capable aircraft without its intended target. What do you do with a Mach 3 interceptor when there's nothing to intercept? The answer, it turned out, was plenty. The MiG-25 evolved into a multi-role platform. Its reconnaissance variant, the MiG-25R, proved extraordinarily useful. Flying at extreme altitude and speed, it could conduct surveillance missions that were nearly impossible to stop. During the 1973 Arab-Israeli War, MiG-25Rs flew reconnaissance missions over Israeli territory that Israeli F-4 Phantoms could not intercept despite their best efforts. The MiG-25 also became a potent symbol of Soviet aerospace capability and a source of genuine Western anxiety. For years, analysts could only speculate about its true performance. Then, on September 6, 1976, a Soviet pilot named Viktor Belenko made a decision that would change everything. Belenko flew his MiG-25 across the Sea of Japan and landed at Hakodate Airport. He walked away from the aircraft and requested political asylum. For the first time, Western intelligence could examine the Foxbat up close. What they found was both reassuring and humbling. The MiG-25 was not the superfighter that Western analysts had feared. Its electronics were relatively primitive by American standards, using vacuum tubes rather than transistors in some systems. Its maneuverability was limited. It was designed for straight-line speed and altitude, not dogfighting. In many ways, it was an aircraft frozen in time, optimized for a mission that no longer existed. But here's what mattered. It worked. Despite its limitations, the MiG-25 did exactly what it was designed to do. It could reach incredible speeds and altitudes. It could intercept high-flying targets. The Soviet engineers had accomplished their mission even if the target had changed. And this brings me to what I consider the broader lesson of the XB-70 story. Both superpowers invested enormous resources responding to perceived threats. The Americans built the Valkyrie because they feared Soviet air defenses. The Soviets built the MiG-25 because they feared the Valkyrie. Both responses were rational given the information available at the time. Both represented genuine engineering achievements, and both were, in some ways, obsolete before they were completed. This is the paradox of the arms race. Each side's actions prompted responses from the other side, creating an escalating spiral of development. The XB-70 led to the MiG-25 and the SA-5. These systems, in turn, influenced American thinking about future aircraft design, eventually contributing to concepts like stealth technology. The Russians developed countermeasures to stealth, and so on. Some historians argue that this competition was wasteful, that the resources devoted to these weapons would have been better spent elsewhere. And from a purely economic perspective, there's validity to that argument. The money spent on the XB-70 could have built hospitals, schools, infrastructure. But I think that view misses something important. The technology developed for military purposes often finds civilian applications. The materials science advances from the XB-70 program contributed to commercial aviation. The engineering techniques developed for the MiG-25 advanced Soviet aerospace capabilities generally. The competition drove innovation at a pace that peace might never have achieved. I also think there's something to be said for the deterrent effect of these weapons. The XB-70 was never used in anger. Neither was the MiG-25 at least not in its intended role. The nuclear weapons they were designed to deliver or defend against were never launched. In that sense, the tens of billions spent on these programs might have been the most cost-effective investment in human survival ever made. This is speculative, of course. You can never know what would have happened if the Cold War had been conducted differently. But I find myself grateful that both sides maintained capable forces, that deterrence held, that the weapons remained unused. The alternative is too terrible to contemplate. Let me now offer some analysis that I think puts the XB-70 in its proper historical context. When we compare the Valkyrie to other Cold War weapon systems, certain patterns emerge. First, there's the question of timing. The XB-70 was conceived in an era of rapid technological change. Between 1955, when the requirement was issued, and 1964, when the first prototype flew, entire categories of weapon systems came into being. The intercontinental ballistic missile went from experimental to deployed. The nuclear submarine evolved from curiosity to cornerstone of deterrence. Satellite reconnaissance became operational. The strategic landscape was transformed. This matters because the XB-70 was designed for a world that no longer existed by the time it flew. It was the ultimate solution to a problem that had already been solved by other means. This is a recurring pattern in military technology. Systems that take a decade or more to develop often face this challenge. Second, there's the question of cost-effectiveness. The XB-70 was extraordinarily expensive. Each aircraft cost approximately $750 million in 1960s money. A fleet of 200 aircraft, which was the original plan, would have cost over $150 billion in today's dollars. For comparison, an ICBM cost a fraction of that and could deliver similar destructive power. But cost-effectiveness isn't the only consideration. There are missions that only manned aircraft can perform. There are scenarios where the flexibility of a piloted bomber provides options that missiles cannot match. The question is whether those advantages justify the expense. Third, there's the question of vulnerability. The XB-70's proponents argued that its speed and altitude made it invulnerable. Its critics argued that Soviet missiles would eventually catch up. Both were probably right. In 1964, the XB-70 would have been very difficult to intercept. By 1974, with improvements in Soviet SAMs, that might not have been true. This points to a fundamental tension in military procurement. Do you build systems that dominate today but might be obsolete tomorrow? Or do you invest in systems with longer service lives but perhaps less impressive, immediate capabilities? There's no easy answer. When I compare the XB-70 to its closest counterpart, the Convair B-58 Hustler, the differences are instructive. The B-58 actually entered service. It flew from 1960 to 1970 as an operational bomber. It was faster than the B-52, but slower than the Valkyrie. It was less expensive, but also less capable. The B-58 demonstrated that supersonic bombers were viable, but also revealed their limitations. The aircraft was difficult to maintain. Its range was limited. Small size restricted its payload. Served for only a decade before being retired, remarkably short operational life for a strategic bomber. Would the XB-70 have fared better? Perhaps its larger size allowed for more fuel and greater payload? Its more advanced design might have aged more gracefully. But we'll never know, because it never got the chance. I want to also draw a comparison to the SR-71 Blackbird, which shares many characteristics with the XB-70 but had a very different fate. Both aircraft were designed for sustained Mach 3 flight. Both used similar construction techniques. Both were products of the same technological moment. But the SR-71 served for over 30 years, from 1966 to 1998. It conducted countless reconnaissance missions. It remains the fastest piloted air-breathing aircraft ever to achieve operational status. Why did it succeed where the XB-70 failed? The answer lies in mission. The SR-71 was a reconnaissance platform. It carried cameras, not bombs. It flew over hostile territory, gathered information, and returned. Its value lay in the intelligence it provided, which was difficult to replicate by other means. The XB-70, by contrast, was a bomber. Its mission was to deliver nuclear weapons. By the early 1960s, ICBMs could do that job more quickly and cheaply. The Valkyrie's unique capabilities, while impressive, didn't justify its cost when alternatives existed. This suggests something important about military technology. The systems that survive are often those that fill unique niches. The SR-71 did something that nothing else could do. The XB-70, despite its magnificence, was ultimately redundant. Now let me address the consequences of the XB-70 program, because they extend far beyond the aircraft itself. For American aerospace, the Valkyrie represented both a triumph and a turning point. It proved that sustained Mach 3 flight was achievable. It demonstrated techniques that would influence aircraft design for decades. But it also marked the end of the big bomber era. After the XB-70, the United States would never again attempt to build a manned bomber that relied on speed alone for survivability. The B-1 Lancer, which eventually entered service in the 1980s, was originally designed as a high-altitude, high-speed bomber similar to the XB-70, but by the time it was built, the concept had changed. The B-1B that actually served was optimized for low-altitude penetrations, sneaking under radar rather than flying over it. The lessons of the XB-70 had been absorbed. The B-2 Spirit took this evolution even further, abandoning speed entirely in favor of stealth. The idea was no longer to outrun enemy defenses, but to avoid detection altogether. This represented a fundamental shift in thinking, one that the XB-70's cancellation had helped precipitate. For Soviet aerospace, the MiG-25 program had similarly far-reaching effects. The technology developed for this aircraft informed subsequent designs, including the MiG-31 Foxhound, which remains in service today. The Soviet experience with high-speed interceptors shaped their entire approach to air defense for decades. The S-200 missile system developed to counter the XB-70 also proved enduring. Variants of the system remain in service with various countries. Its design influenced subsequent Soviet and Russian SAM development. The investment made in response to a threat that never materialized nonetheless yielded capabilities that proved useful in other contexts. Perhaps most importantly, both programs contributed to the scientific and engineering knowledge base that continues to advance aerospace technology today. The thousands of engineers who worked on these projects gained expertise that they carried into subsequent work. The techniques they developed, the problems they solved, the lessons they learned, all of this accumulated into institutional knowledge that shaped the industry. I want to conclude with some personal reflections on what the XB-70 means to me and what I think it should mean to us today. When I look at the Valkyrie, I see human ambition at its most audacious. Here were people who looked at the laws of physics and said, "We can work with that." They faced engineering challenges that seemed insurmountable and surmounted them anyway. They built something that had never existed before, something that pushed the boundaries of what was considered possible. Yes, the XB-70 was a weapon of mass destruction. Yes, its purpose was to deliver nuclear annihilation. I don't minimize those facts. But I also recognize that the engineers and scientists who built it were not motivated by destructive impulses, They were solving problems, pushing limits, achieving what seemed impossible. That drive to exceed our grasp is part of what makes us human. I also see in the XB-70 a cautionary tale about the arms race. Both superpowers invested enormous resources in this competition. The Americans built the Valkyrie. The Soviets built the MiG-25. Both programs consumed billions that might have served other purposes. And in the end, neither aircraft ever faced the other in combat. The chess pieces were never captured because the game was called off. Was it worth it? That question haunts discussions of Cold War military spending. Some would say no, that the money should have been spent on human needs. Others would argue that these investments preserved the peace, that deterrence required credible capabilities, that the absence of superpower conflict was purchased at this price. I find myself torn. The waste troubles me. The opportunity costs are real. But I also recognize that we don't live in a world where military power is irrelevant. Nations need the ability to defend themselves. Sometimes that means building weapons that will never be used, capabilities that exist solely to deter aggression. What strikes me most about the XB-70 today is how thoroughly it has been forgotten by the general public. This aircraft, which represented the cutting edge of human technological achievement, which cost billions of dollars, which prompted the Soviet Union to restructure its entire air defense system, is now a museum piece that most people have never heard of. It exists in photographs and flight footage, and the memories of those who saw it fly, but its story has faded from public consciousness. I think that's a loss. The XB-70 deserves to be remembered, not as a triumph or a failure, but as an example of what humans can achieve when they commit themselves to a goal. It should stand alongside the Apollo program and the Manhattan Project as a demonstration of technological capability. And perhaps most importantly, the XB-70 should remind us that history doesn't move in straight lines. The future that seemed inevitable in 1955, a future of Mach 3 bombers and orbital battle stations and routine supersonic travel, didn't materialize. Instead, we got ICBMs and spy satellites and stealth aircraft. The path of technological development is neither predictable nor predetermined. If you've made it this far, I genuinely appreciate your attention. This story is one that I find endlessly fascinating, and I hope I've conveyed some of why. The XB-70 Valkyrie represents a road not taken, a vision of the future that was superseded by other visions. But for a brief moment in the 1960s, it was the most advanced flying machine ever created, a testament to human ingenuity and ambition. Today, only one XB-70 remains, displayed in the Cold War Gallery at the National Museum of the United States Air Force. If you're ever in Dayton, Ohio, I encourage you to visit. Stand beneath those enormous wings. Look up at that impossibly sleek fuselage and think about what it represents. The dreams and fears of an era, the technical brilliance of its creators, strategic calculations of its sponsors, the Soviet engineers who built machines to counter it, the test pilots who risked their lives to prove it could fly. The XB-70 could have changed history. In a sense, it did, just not in the way its designers intended. The Soviets built an entire fighter fleet to stop an aircraft that would never attack them. The Americans proved that Mach 3 flight was achievable, and then decided they didn't need it. That's the paradox of the arms race. That's the legacy of the XB-70 Valkyrie. And that, I think, is a story worth remembering.